Hello, how are you? Welcome to the CurioClips channel. When you think of glaciers, what comes to mind is an image of a vast expanse of ice slowly moving across the landscape, carving out valleys and leaving behind a moraine of rocks and dirt. But that's only half the story because glaciers don't just move across the land. They can also move up and down. And in the past, they've done more than that. In fact, during the Earth's history, there was a time when the entire planet was covered in ice, so much so that it has been nicknamed the Snowball Earth. So why did this happen? And how did life survive? So the first thing we should do is break down how much ice we're talking about here. Well, there are two different ways to answer that question. There's how thick was the ice and how much of the Earth was covered by it. For the thickness, estimates vary from a few dozen meters to more than a kilometer in some places. The ice would have extended far inland, too, not just along coastlines. But for how much of the Earth was covered, geologists estimate that something like 90% of the planet was under a kilometer's worth of ice. That would be around 60 trillion cubic kilometers of ice. To put that into perspective, that's enough to fill up 24 million Olympic-sized swimming pools or 12 million African juice boxes. This happened twice in the Earth's history, once at around 635 million years ago, and again at around 716 million years ago. It is thought that these events caused a mass extinction with more than 80% of all species disappearing after the first one and more than 90% after the second. But hold on, if most of the Earth's surface was frozen solid, how could life have survived? How did those pesky little critters get their body temperature up to function if their environment was an ice cube? Well, the good news is there is plenty of heat below the ice. We know that because we have direct observations of the interior of the Earth today. So let's take a look inside. The inner core of the Earth is estimated to be between 5,200 and 6,370 degrees Celsius. Then there's the outer core, which ranges between 700 and 5,200 degrees Celsius. Then comes the mantle, which is between 1,000 and 3,700 degrees Celsius. Finally, there's the crust, which ranges from 0 to about 1,000 degrees Celsius. The average geothermal gradient is around 3 degrees Celsius per 100 meters, with an average heat flow of 2.5 watts per square meter. In other words, the deeper you go below the surface of the Earth, the hotter it gets. This is why geothermal energy is a thing. We harness this energy to generate electricity without producing any greenhouse gases. But let's take a closer look at the crust. First, let's take a look at an area without a bunch of ice on top. If we ignore the parts with magma, the layer of rock near the Earth's surface where liquid water can exist is called the lithosphere. It goes down around 100 kilometers. Below the lithosphere is the asthenosphere. These two layers together make up the rigid part of the Earth's crust. But back to the surface, the lithosphere has a variety of different temperatures depending on how much sunlight hits it. During the day, the top layer will be warmed by the sun, so the top layer will be around 15 degrees Celsius. Below that will be around 10 degrees Celsius, then 5 degrees Celsius, and then it reaches the freezing point of water at 0 degrees Celsius at around 2 meters below the surface. Now let's imagine that this whole area is covered in a 100-meter thick layer of ice. That means that the top layer of the ground beneath the ice would be at around 5 degrees Celsius, the second layer at 10 degrees Celsius, and so on. So as you can see, there is still a lot of heat coming from the Earth's core, and it's enough to keep the ground beneath the ice from freezing solid. Now let's add another 90 kilometers worth of ice on top of that, which is how thick the ice sheet would have been during the Snowball Earth event. The temperature profile changes slightly, but there is still enough heat coming from the Earth's core to keep the ground from freezing. In other words, although the surface of the Earth would be frozen, the bottom of the ice sheet would be above freezing. Exactly how much above depends on how much sunlight hits the top of the ice. But assuming a reasonable amount, we're talking about several degrees above freezing. So how does life survive conditions like that? Well, it turns out that some creatures actually prefer it that way. Take, for instance, tardigrades. Tardigrades are microscopic animals that live in water. They can survive in a wide range of habitats, including hot springs, deserts, and even outer space. But despite their ability to adapt to extreme environments, tardigrades need at least some liquid water to survive. Take the Antarctic as an example. During the winter, temperatures there can drop as low as negative 60 degrees Celsius. But even in those frigid conditions, there is still some liquid water present. This is because the ocean water doesn't freeze all the way through. Instead, it forms a layer of ice on the surface that acts as an insulator, preventing the water below from freezing. And underneath that layer of insulating ice, the temperature stays at around 0 degrees Celsius. As long as there is enough water present, tardigrades can survive. Now let's apply this to the Snowball Earth. The same thing would have happened. There would have been a layer of ice on the surface that insulated the water below. Plus, we know that during the Snowball Earth, carbon dioxide levels were higher than they are today. Carbon dioxide is a greenhouse gas, which means that it traps heat in the atmosphere. The higher the carbon dioxide levels, the warmer the planet. So although the surface of the Earth would have been frozen, the bottom of the ice sheet would have been warm enough to support life. But wait, if carbon dioxide is a greenhouse gas, wouldn't the Earth have been able to trap more heat and avoid freezing in the first place? And the answer is yes, it could have. But it seems like there was a tipping point that once crossed couldn't be uncrossed. We'll tell you about that next. There are several hypotheses as to why the Snowball Earth occurred. One theory is that the continents were located close to the poles, leading to a decrease in global temperatures. When the continents are near the poles, the amount of solar radiation they receive is less than when they are near the equator. This is because the angle at which sunlight hits the Earth's surface affects how much energy is absorbed. When sunlight hits the Earth at a shallow angle, it spreads out over a larger area and is thus less intense. Additionally, the axis of the Earth relative to the Sun changes over time. The Earth wobbles on its axis like a spinning top, and this wobble affects how much solar radiation different parts of the Earth receive. When the axis is tilted away from the Sun, temperatures drop. These factors combined to create a snow globe effect. The ice sheets reflected more sunlight back into space, which lowered global temperatures. Eventually, the temperatures dropped below the melting point of ice, and the entire planet froze over. Another hypothesis is that there was a runaway greenhouse effect that lowered atmospheric carbon dioxide levels. When carbon dioxide levels are high, the Earth is warmed by a greenhouse effect. As temperatures rise, more carbon dioxide is released from rocks and oceans, which further increases the greenhouse effect. This positive feedback loop can lead to runaway greenhouse conditions like we have on Venus. But the Snowball Earth was the opposite, a runaway icehouse effect. As temperatures dropped, more carbon dioxide was locked away in rocks and ice, which reduced the greenhouse effect and further lowered temperatures. This negative feedback loop can lead to an icehouse effect, where temperatures drop so low that the entire planet freezes over. A third hypothesis is that volcanic activity decreased, leading to lower levels of greenhouse gases in the atmosphere. Volcanic eruptions emit carbon dioxide and other greenhouse gases into the atmosphere. If volcanic activity decreases, greenhouse gas levels may drop and temperatures may cool. We don't know exactly why the Snowball Earth events happened, but we do know that both events were followed by a rapid warming period known as a hothouse period. During these periods, temperatures rose quickly and the ice sheets melted. The exact mechanisms that caused the warming are unknown, but it's thought that a combination of factors led to the rapid change in climate. So the Snowball Earth is a remarkable example of how the climate system can change over time. It shows that even small changes can have big effects and that the climate is always in flux. Now watch what happens when a glacier melts or check out this video instead. Thanks for watching.